So good morning, everybody, and thank you, Christian, for this kind introduction. So today we will discuss about turbocharger integration into a fuel cell system using GT Suite simulation. So as an introduction, let me present you our system for heavy-duty trucks. So as you may know, a fuel cell system is composed of a fuel cell stack, where the hydrogen and oxygen will be transformed into electricity. And in the system, we have some auxiliaries to condition the gas to have better performance and efficiency. And in this specific case, we have a E-turbo compressor to increase the pressure of the system, the pressure of the air inside the system, an intercooler to cool down the air, and a humidifier to get the air at the right level of humidity. So the two main advantages of the turbocharger compared to the E-compressor will be to recover some energy from the exhaust gas, so we will reduce the electric consumption of the compressor, and we will also increase the overall pressure of the system to increase the efficiency of the stack itself. So for that presentation, I will have three main parts. The first one will be the key parameters for correlation to test data. Then we will check the performance of our E-turbo compressor compared to our previous compressor, and some slides about system architecture and operation optimization. So for the correlation, the first step of the construction of the model is to build a stack model. It's a very simplified one with simplified anode, cathode, and cooling loop. And the main parameters that are very important for model correlation are pressure losses versus mass flow and water balance. So I recommend two tests to correlate a stack model. The first one is a UE curve test, also called polarization curve, where you sweep the full range of current and, if possible, in various operating conditions. The second recommended test is a pressure sweep out of the stack, and specifically for this turbocharger integration, because the turbine at the exhaust will vary a lot the exhaust pressure, and you need to have a stack model with the pressure loss, which is very well correlated to test data to have a good prediction behavior. So here I share some results of the stack model. So on the left, you can see that the pressure at cathode inlet, so at air inlet, is very close to the data for the full range of current. And on the second graph, you can see also that the dew point out of the cathode, so the humidity, is also well predicted by the model. Then we can review the pressure sweep test together. So on the x-axis, you have the outlet air pressure, and on the y-axis, you have the inlet pressure response. So you can see that the GT Suite model is very well correlated to test. And then also another thing which is very important is to catch the impact of the outlet pressure on the stack voltage. Here, you can see that if you increase the outlet pressure, you will have an increase of the voltage, meaning you will have a better stack efficiency. As a result, you can see that we can predict the UE curve quite well on this stack model. So this model is now ready for integration into the full system model. Here I present this system model, so you can see that we still simplified the anode and cooling loop because I focused on the air loop. And even in the air loop, I did some simplifications. So I simplified the air filter, the intercooler, and the muffler, but I put more details on the compressor, turbine, and humidifier in order to still have the right pressure loss prediction and water balance prediction. Again, these are the main parameters for model correlation. Here are the results of the system model. So as you can see, the pressure drop along the air pass is very well catched by the model. So we have each component which are at the right level of pressure depending on the operating point. Here it's at max current. We have less than 3% deviation. Another very important thing is to catch the turbocompressor electric consumption. There are three main factors taken into account: the compressor mechanical power, the turbine mechanical power, and the inverter efficiency that drives the electric motor for the turbocompressor. Here again, we have a quite good correlation. And as a result, we can predict the UE curve of the full system model with a high level of confidence. So now this model is considered ready for further system architecture or control optimization studies. Let's check now the performance of the system. Here on the left graph, you have many information. So in green, it's the E-turbo compressor results, simulation versus test. In orange, you have the E-compressor system, simulation versus test. And the data which is plotted here is the net system efficiency. So the first result is that the model correlation is quite good, with less than 2% deviation between test and simulation. And also, the second result is that we can save up to 2 points efficiency at maximum current using the E-turbo compressor compared to the compressor. And in the same time, we increase the overall pressure of the system by 450 millibars. So now I would like to present some architecture studies that we run with this model. So on this left graph, you can see the impact of the ambient conditions on the net system power output. So this is a very important feature of the model because we cannot run easily some ambient tests. Here we can simulate altitudes, temperature, and so on. So in that case, if you focus on the orange curve, which is here, you can see that using the turbo compressor, from the reference conditions at sea level and 20 degrees C to the worst case 2,000 meters of altitude and high temperature, we lose up to 6% net system power. As you can see, we have exactly the same trend with the E-compressor, but here the advantage, as we increased the outlet power, even in the worst case of altitude, you are still at the level of the reference with the E-turbo compressor. So this is very interesting. And on a second graph, there is another parameter that we need to take care, is the compressor out temperature. So here you can see that between the reference point and the worst case, we could increase the compressor out temperature by up to 40 degrees C. And this will have a non-negligible impact on the intercooler design and the heat rejection to the cooling system. So with this kind of simulation, we can re-specify the intercoolers or the cooling loops. A second work that we performed with our GT Suite model is to optimize the matching between the compressor and the turbine. Here you can see on the right, at high current, two different kinds of matching, so the different kind of compressor and turbines. You can see that in the red case, our max current operating point is very close to the maximum capacity of the compressor, so we could say that the compressor is well sized in this system, but the efficiency won't be optimal, as the efficiency is better in the center of the map. So here, the second matching, you have a slight oversized compressor, but you have a better efficiency. And we can also quickly check with the model that at low current, we are not too close to the surge line that can deteriorate later the compressor. So it's a very good tool to assess very fast different kind of matching and to optimize the turbo compressor to our architecture. And here I have a concrete example. Here on the right, you can see the net system power between the two matching. And the surprise is that matching 1 and matching 2 offers exactly the same outlet net power, but the stack will operate in very different conditions. For the matching 1 in blue, you have a much higher pressure at stack inlet, but the stack will operate at lower humidity. And in the second matching, you can see that it's the opposite. The pressure is lower, but the humidity is higher. So depending on your stack technology, and especially the MEA which is inside, some are more tolerant to water, more tolerant to pressure. So you can adapt the air loop to your stack technology. And using GT Suite is very fast and very convenient. Okay, so as a conclusion, we showed that the main correlation parameters for this kind of air loop design optimization are pressure losses prediction and water balance prediction. Now our internal model is robust enough to support the engineering teams in developing the air loop, and especially in two main domains. First, performance and efficiency assessment and optimization on the current architecture. We can work on operating conditions or turbo compressor matching quite fast. And as a second step, we can run some architecture optimization. So I presented the matching before, but we can also imagine as next step to evaluate the single stage versus two stage. We can also specify components like the intercooler or the humidifier, depending on the performance and efficiency targets. We can evaluate some idle and low power strategies because you need to regulate your system, to control the system. And we can also perform further studies in component design, like the bearings for the turbo compressor. You can study standard bearings, hair bearings, and so on. So at the end, once your model is well correlated, you have a great tool to perform fast optimization before validation on the testbed. Okay? So thank you for your attention. And if you have some questions, I would be happy to discuss them with you.
Thank you, Gauthier, for the interesting presentation. Are there any questions for Gauthier based on this?
Yes?
Thank you. I have a question. How do you explain the difference of humidity while you have, I imagine you have the same inlet conditions and you have same compression ratio, since you have the same
yes.
consumption?
So here the idea of the study was to evaluate the best matching for the at ISO net outlet power. So if you increase the pressure of the system, then you will have a higher outlet power from the stack itself. So you need to compensate somewhere. So you can reduce the humidity to keep the same net outlet power. So it's a compromise. If you increase the pressure, you increase the power, so you can reduce the humidity to get the same performance or the reverse conditions. Yeah.
Any other questions?
Yes?
Oh, sorry.
Ah.
Hi, thank you for the presentation. Quick question regarding transient points, because most of the work you've done focus on steady state.
Yes.
Is that correct? Can
Yeah.
you give some comments? How would you model that transient and how the control response will be like?
So at the moment, we only focus on steady state because our target was to specify the components and check the performance and the behavior between the different components. So now we are currently started to run some transient tests internally, and it will be a next step of our simulation. Yeah, but the first tests are promising. So yeah, let's see in the model how it will behave.
And yeah, thank you again, Gauthier.
Welcome. Oh. Thank you. Thanks a lot. Thank you.